Welcome, welcome. This is Chapter 3, Unit 3, Power Functions and Polynomial Functions. Maybe the book has it, Polynomial Functions and Power Functions. I don't know if they changed that, but it should be Power Functions and Polynomial Functions. Anyways. So, first thing, identifying power functions. We're going to have a look at power functions first. So identifying power functions. Notice that a power function takes the form f of x equals k xp. See if I can zoom in. There we go. K and p are real numbers. So k is a real number and p is a real number. X would also be that would be a variable. So this is an x as you would normally see it. So it's a variable raised to a fixed power, like f of x equals x squared. That fixed power is 2. Half x to the 20th, that's also a power function. These can be pieced together to make other functions, which is why we're going to go ahead and have a look at the power functions. So the end behavior of power functions. When we are going to describe the end behavior of a graph, what we're going to do is we're going to talk about, if we were to look at a graph, we're going to talk about what happens as these values go to their extremes. And that's just the x values. So we're going to, you'll hear common terms would be, so if x is going to go towards infinity, so if it's going to go this way, it's going to get big, 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 big. You would say, sometimes you would hear x increases without bound, or as x tend towards infinity, or as x approaches infinity. For the other direction, you would hear as x decreases without bound. What that without bound means is that we're not stopping how much it decreases by. We're just letting it go. Or you could say as x approaches negative infinity, or as x tends towards negative infinity. The way you will see it written, it would be something like this. And you could read that arrow as approaches. So as x approaches infinity, or as x approaches negative infinity. These all stand for the same thing. So one thing we're going to have is we're going to have a look at even functions first, because I prefer even numbers. They're nice. I like it when I can break things up pretty easily. So even functions have end behavior that will be the same on both ends. And these are power functions that have an even power. So 2, 4, 10, 100. If it's an even number, it's going to be an even power function. So what we will see, and you can see from this table below, that both of the even functions, the end behavior will be the same. So it's just mirrored on both sides. And we are going to have a look at some even functions. So if we had, let's start with f of x squared. Oh, I have to put equals. I'm getting way ahead of myself here. Equals x squared. That don't look quite right. Equals x. There we go. Squared. And then we can have h of x can equal x let's say to the power of 16. That looks good. And now let's take it to an extreme. So we're going to say g of x equals x. What can be really big to a super extreme? You know what? We're going to use my elementary school ID that you would have to punch in your elementary school lunchroom, 261778. I legit still remember that. I don't know if you guys still remember your elementary school ID. I totally do, and I'm 30 years old. So 261778. Etheridge Elementary in the house. Okay, so one thing we are going to notice is first notice that it has no coefficient. So everything in front of the x is a 1. So we're going to notice that when we have a positive even function, such as, x squared, x to the 16th, x to the 261,778, this is what it will look like. So notice that the end behavior is the same. So as we have our x going off in the positive direction, our y is going to go off in the positive direction. And if we have our x going off in the negative direction, our y, once again, is going to go off in the positive direction. And another thing to note is, as the power increases, if you look at that curvature at the origin, it gets flatter and flatter and flatter and flatter and flatter and flatter and flatter. Let's see if we can zoom in. Ooh, we're gonna have to zoom in a lot. Now notice when you do zoom in, it's not actually squared off. It is still a curve, but it just gets extremely flat at the origin. And let's zoom in even more. See, it is still indeed a curve. It just gets flatter and flatter and flatter. And those are the what that looks like. Now, let's say I made them all negative. All right, so I made them all negative. Notice that flips it over the x-axis so that now, instead of when our x's go off in the infinite directions, both negative and positive, our y is going to now become super negative. So as x goes off into the negative infinity direction, our y is going to go negative infinity. And as the x goes positive infinity, our y is going to mirror the other side and go towards negative infinity also. So in just a simple even power function that is negative, you will not be getting a positive value, if that makes sense. And notice it does not change the shape of things at all when we're talking about that curvature. So let's see. So yes, it does flatten near the origin. This is when we have a positive. Notice from our graph down here, if we had f of x equals k x to, what were we using, a? P, we were using p. K x to the p. So notice that when this is negative, it does actually flip over this x-axis. So that's what we were looking at. This is the notation for how you would describe end behavior. So you have to state which direction your x is going, and then you also have to state which direction y is going as a consequence of your x. So now let's have a look at odd functions. So first thing I'd like for you guys to notice, because some students don't think of it like this, Notice that our linear function is actually a power function. It's a power function where our power is just 1. And we're going to have h of x is equal to x to, we'll do the 17th. Oh, I need a caret. We'll do 17th. And then we can have one that is, oh man, super negative or super odd, super big odd. Let's think of a super large odd number. What's super big odd large number 2? I know. I don't know. I'm just going to 58, 58, 7. That looks good. And that's an odd number because, you know, 7 is not divisible by 2. Okay, so let's have a look at what happens here. So the first thing I notice is that they don't go in the same direction. They actually go in opposite directions. So that means as my x gets larger and larger and larger, my y is going to get larger and larger and larger. And as my x gets smaller and smaller and smaller, smaller, more negative, my y is going to get more and more and more and more and more negative. Also, notice that, let me zoom in, as we increase the power, we still see that flatten out at the origin. And if we zoom in, we can see that there is still curvature. It does not actually create a box. So this is exactly what happens at the origin with our even functions. They're going to flatten out for the higher power they are. Notice that odd powers switch at the origin. So if we were to take, if I were to just take x to the 17th, I would notice that, you know, as x gets larger and larger and larger, y gets larger and larger and larger. As x gets more negative and more negative and more negative, y will also get, you know, smaller and smaller and more negative and more negative. That is an odd function. Now let's have a look at what happens if we were to make this negative. Boom, it flips. So let's go ahead and make all of these negative. Now notice, when you have a negative odd power function, it's the opposite of the opposite, I suppose, if that makes sense. So as your x gets larger, your y gets smaller, and as your x gets smaller, your y gets larger. That's what happens if you make them negatives. They also do flatten out at the origin, like we did say. And this is when k is greater than 0. So you can see an instance in this particular one of what happens when k is positive versus when k is negative. When it is positive k, they will both, notice they both go in the same direction. When it is negative k, notice that these guys will go in the opposite direction. So x will go in the opposite direction of y, and y will go in the opposite direction of x. What that means is if x gets large, y gets small. If y gets large, then x gets small. Now we will identify polynomial functions. Now a polynomial function is sort of like a grouping of these power functions. And these are the polynomial functions are probably what you're most used to. A quadratic function is a polynomial function. This is the general form. We are right here. This is the general form of a polynomial function. All of the coefficients, the ANs, are real. Each power is a non-negative whole number. So we can't have x to the half, which is like a square root. So we can't have any square roots in here. Notice that the powers are also arranged so that they are decreasing. So that means if I give you something along the lines of f of x equals 12x4 plus x to the 6 plus x minus 1. You would need to rearrange it in order to, I think, read it better. The proper order would be this. And there will be some things in here that you are going to have to put it in the proper order, or it is not necessarily going to work. So identifying the degree and the leading coefficient of a polynomial. The degree, that's the first thing we're going to look at. The degree of a polynomial is the highest power. That means if we were given this polynomial, the degree is 12. That's the highest power. So in our example up here, it would be a 6th degree polynomial. This one is a 12th degree polynomial. The leading term is the term containing the highest power. So for us, it's 16x to the 12th, and that's from this function right here. And that's the leading term. The term is when you just take everything that is between your operation signs. And what I mean by that is a term will be separated by some type of basic algebra. Each one of these is a term. Like this polynomial that we have here is 1, 2, 3, 4, 5, is 5 terms. The leading term is the one with the highest power. That's why it's really preferential that you guys kind of write them in the correct order of power. Now we have another definition. The leading coefficient is the coefficient of the leading term. So that's just that number that is associated with the first term. Whatever we're multiplying that first term by. So when we are going to determine the end behavior of polynomials, which is a whole group of power functions, you have to look at the leading term, because if you were to increase your x, your leading term is the one that would take over. You can think of it like a family. If you were out with your family on vacation and dinosaurs attacked, or Will Smith in a spaceship came down like Independence Day and blew up the White House. I mean, if some catastrophic event happened, you can consider your family sort of like a polynomial. Each of you is of a certain degree, so you are of a certain age. And in a catastrophic type situation, it would be assumed that the oldest, so the child with the highest degree, the highest age, would take over and dominate the rest of the group in an effort to save everyone. That's how you can think of a polynomial. That highest power is just going to take over the rest of the polynomial, so that if a decision has to be made, it depends on that highest powered term. I don't know how many of you are the oldest, but I think I'm the oldest girl, so people kind of rely on me for girl stuff, like planning Christmases. So when we're going to determine that end behavior, so for our example, right here, if I were to take x as 1,000, notice that that first term just gets ridiculously large, and it actually gets much larger than the term next to it. So when it comes to finding the value of y at that x value, it's gonna really rely on that first, oldest to say term, the one with the highest degree. So here's an example. We are going to describe the end behavior and determine a possible degree of the polynomial function. Well, the first thing I notice is that they go in opposite directions. So that makes it an odd degree. So it's the highest degree is going to be odd. What I do notice is that as x gets larger and larger and larger, y also gets larger and larger and larger. And as x gets smaller and smaller and smaller, our y is going to get smaller and smaller and smaller. So this means that our coefficient is greater than 0. If it were less than 0, we would see this flipped like this. But it's not. So we can say with certainty that our k is going to be positive. So when it says describe the end behavior, that's what I just did here. And that's all you have to do. Don't really even have to put it in words. And when it says determine a possible degree of the polynomial function, that is this. That's all you have to say, is it's an odd degree. You can list an example, it's an odd degree such as x3 or something, or x17. I mean, it doesn't matter. But all you have to do is say odd. So now we're going to describe the end behavior and determine a possible degree of this polynomial function. The first thing I'm going to notice is that the ends go off in the same direction. So it's going to be an even degree. So as x gets larger and larger and larger, y, our f of x, is going to get smaller and smaller and smaller. And as x gets smaller and smaller and smaller, our y again is going to get smaller and smaller and smaller because of the symmetry. So notice that this does not look like a standard x squared. This looks like a negative x squared because it is flipped. So I know our k is going to be less than 0. So once again, my end behavior was described using this. And my possible degree, it's okay if you just say even. So another thing that interests us as math people is determining the changes of a graph. So when something changes. So those are things like turning points, like in a parabola where it goes back on itself, the vertex. Another interest of us is if y is equal to 0. So if we have a x-intercept, or if x is equal to 0, if we have a y-intercept. Those are things that are very important to us. So interested in turning points and interested in intercepts, both x and y. So we're going to do this here. Try it number 6. So we're given this polynomial, and we are going to determine the y and the x intercepts. So if we wanted to determine the y-intercepts, that would be places along y. So then we know that our x is going to equal 0. Well, here, notice that when x equals 0, we get 2 0 cubed minus 6 times 0 squared minus 20 times 0. I mean, like, that's just 0. So we're going to have 0, 0. So that's an intercept. This is our y-intercept. Now for an x-intercept. I am going to go ahead and start factoring this because that is one of the things I have to do. And I'm going to take out an x. Actually, I will take out a 2x. There we go. I'm going to take that out. So now I'm going to factor the inside. This is how I do it. And yes, I can't do it in my head. So sorry, guys. For those of you that can, wonderful. But I cannot. So do whatever you need to do to make sure you get the right answer. Except for cheating. Don't do that. So we're going to have -5 and 2. So that gives us, and I'm going to break it down into, we'll do 2x minus 5x minus 10. And that will give us x times x plus 2 minus 5 times x plus 2. So now I have 2x, x plus 2, x minus 5. Set everything equal to 0. So my x-intercepts are when x equals 0 from this one, when x equals -2 from this one, and when x equals 5 from this one. So what does that give me? Well, I'm going to have to plug these back in. So I know that I already have 0, 0 from right here. So I don't even need to do that one. So now I have -2. So we're going to have 2, -2 to the 3 minus 6 to the -2 minus 20 to the -2. So that gives us 2 times -8. Was this one squared? Minus 6 times 4 plus 40. -16 minus 24 plus 40. And this is going to give us, so it's going to be 0. So y is 0. Of course. Oh, right. Y is 0 for all of these, duh. So that makes -2, 0, 5, 0. So now the degree is what we're going to go ahead and look at. So again, those intercepts are important. And usually you'll be given something like this where you will have to factor multiple times. I'm just going to give you guys a warning. The degree of a polynomial will help us determine the number of turning points and x-intercepts. So notice that if you have a degree n, you will have at most n roots and n-1 turning points. So for our function above, 2x cubed minus 6x squared minus 20x, the most we could have, the degree, was 3. Notice we had 3 x-intercepts, which went along with our theorem perfectly well. And we will have 3 minus 1, so we will have 2 turning points. So 2 humps, I guess, 2 vertexes where it will change. So without graphing this function, this is try at number 7, we are going to determine the maximum number of x-intercepts and turning points. So notice it's not in proper order, so I'm going to write it in proper order. The largest one looks like 14x12 minus 13x to the 9th minus 8x to the 4th plus 2x to the 3rd plus 108. And this is what it looks like. So the highest power, our degree, is 12. So that means the maximum number of x-intercepts is going to equal 12, and the turning points are going to equal 11. Now let's have a look at this one. What can we conclude about a polynomial represented by the graph shown here? And actually that looks like the end. Okay. We'll do this one and then we'll move on to some examples. Now, what can we conclude about the polynomial represented by the graph shown here based on its intercepts and turning points? Well, notice that we have 2 of these turning points. So if our n minus 1 equals 2, this is turning points. So that means our n is going to be equal to 3. So we're going to have a third degree polynomial of some type. Its intercepts. Notice that we have 3 of them. And we will have n intercepts, which matches up with the 3 we found earlier from the turning points. Now, this is sufficient for this question, but I'm going to one-up you. What can this tell us about the coefficient in front of that term? Now, based off the n behavior, I have as x approaches infinity, our y is going to approach negative infinity. And as x approaches negative infinity, our y is going to approach positive infinity. Now, what does that tell us about that k? Well, if we go back and we look, notice that when k is positive, we'll have something like this. But this is the opposite. As our x gets larger, our y is not getting larger, it's getting smaller. So what this can tell us, what the end behavior can tell us, is that k is less than 0. And this is how you would go about analyzing a graph. Okay, so we're going to describe in words and symbols the end behavior of f of x equals negative 5x to the 4th. So notice that x to the 4th, that's an even power, so they would both go in the same direction, but it's a negative k. So they're both going to, I don't know what it looks like. It's going to be some loop-de-doop-de weird stuff in the middle. You know, the ones that are like, ugh. So I don't know what it's going to look like in the middle. I have no idea. I have not graphed this. But this is what the end behavior is going to do. So in words, you would say as x gets larger, our y gets smaller, and as x gets smaller, our y gets smaller. But I'm more concerned with symbols, that you guys understand like the concept and that you can convey the concept. And symbols is enough for that. So as x goes to infinity, y goes to negative infinity. As x goes to negative infinity, y goes to negative infinity. And this is enough for me. Okay, so 13 through 15, we need to determine if the function is a polynomial, and we need to give the degree and the leading coefficient. So let's have a look here. Do all of them look like polynomials? Well, 13 does. Ooh, what about this guy here? Let me zoom in a little. What about this x plus 1? What is that? Get that out of here. Not a polynomial. And this guy is also a polynomial. Okay, so we're good. So it wants the degree and the leading coefficient. Here, the degree is 5. Oh, that's not at all what I said. Sorry about that. The degree is 5, and the coefficient is 4. Here, notice we will have to multiply this through in order to get the highest degree. So here, after we do that, we're going to get 4, and our k is going to equal a positive 1. So one side note I will make about these for number 13, where we have n equals, is it 3? No, 5. N equals 5 and k equals 4. If we were talking about n behavior of a graph, so the 5 would mean it is odd. So k is a positive number, So our end behavior would do something like this. I don't know what it would do in the middle. I'm sure it'd do something absolutely ridiculous. But I don't know. Yeah, I don't know. All I do know is that the end behavior. What this also tells me is that we will have 5 intercepts. So it will cross at 5 points. I don't know what they are. I'm just kind of guessing. And it will have 4 turning points. So it will have 4 vertex-like points. If we were to look at number 15, that's an even function. Notice that our k is positive, so it will do something like this. Now, it'll do something weird in the middle. I don't know what it'll do, but I can guarantee you it'll do something weird. Polynomials are weird. So, and what that tells me is that I'm going to have 4 intercepts, and I will have 3 turning points. So here, if I want to determine the end behavior of the polynomial function, notice my highest degree is 4. That means, and its k is 2, so k is positive. So it's even. So as x gets large, y gets large. And as x gets really small, y is also going to get large. Number 17, I'll let you guys do that one because that one's kind of similar. Now here, when we multiply everything out, we're going to get 2x squared plus 6x cubed minus 2x to the 4th. Rearranging that, that's what we get. So now looking at the leading term, that leading coefficient is -2, so that's going to make it flip over the x-axis. The degree is 4, so we will get something like this, which means as x gets larger, y gets more negative, and as x gets more negative, y gets more negative, or tends towards negative infinity. Trying to put it in normal conversational like speech. It's easier to convey math that way remotely. So this was 3.3. Here we go. Yes, this was 3.3. I will see you in the next one for 3.4.